This is one of a series of lectures produced by the Further Mathematics Support Programme for A-Level Mathematics Revision. In this lecture we're looking at the Edexcel Decision Mathematics 2 specification, and the topic is game theory. The specification says that you should be familiar with the two-person zero-sum games and the payoff matrices for these. And then for all these matrices you should be able to identify play-safe strategies and whether or not there are stable solutions, sometimes known as saddle points. You need to be able to reduce payoff matrices using dominance arguments, and then look for an optimal mixed strategy for a game with no stable solution, and that would be done by graphical methods. And finally, you should also be able to convert 3x2 and 3x3 games to linear programming problems. Well, to go through the main ideas then, here's a typical payoff matrix for a two-person zero-sum game. So remember that the matrix is normally done in terms of player A, and here we have players A and B that each have three different strategies. The numbers in the middle of the matrix, those give the expected gain to A for each of the different strategies played by A and B. So for example, the 5 in the position A to B1 means that if A plays their choice 2, their strategy 2, and B plays strategy 1, A will gain 5 units. The idea of dominance is that a matrix can sometimes be reduced because there's no point one of the players using one of their strategies. So in this example we can see that player A would be worse off compared to playing A3 compared to playing A1. In all cases the numbers in the row A1 are greater than those in A3. So dominance says, well, we can ignore A3 because player A is never going to use those. And we would say that row A1 dominates A3. A similar argument could be applied for player B, but this time of course you would be looking for a column where the numbers are always less than those in a different column. And in this particular case there's no such column existing, so there's no dominance argument that can be applied here for B. The play-safe strategy is one where each player is trying to make their worst outcome as good as possible. So for player A we look at the smallest value in each row. So the row minimum values, in this particular case 3 and -1, and we want to maximize that. So A wants to say that the worst case scenario is that they gain the largest amount. So this is what's called the maxi-min value. For B, the play-safe strategy is that A's gains, a maximum gain, is as small as possible. For that, therefore, we look at the column maximum values, which are 5, 4, and 5, and we find the smallest of those. So for B we want the mini-max value. If the maxi-min value, the row maxi-min, is equal to the column mini-max values, then we have what's called a stable solution, a stable strategy, in which case there's no point A or B changing their chosen strategies, which are shown here of A1 and B2. However, in this particular case the numbers are different, and therefore we have an unstable solution to the problem, and we can therefore look at going to the next stage, which is to see whether they can actually do better some cases. So A may decide that instead of playing A1 on some occasions we'll play A2, and B may decide, well, instead of playing B2 they will play B1 or B3. What we want to decide then is with what probability should they do that. Well, if we start off by looking at A, we let A play strategy 1 with probability P, and therefore strategy 2 with probability 1 minus P. And then we look at what would happen in the cases of B playing B1, B2 and B3 in turn. So for B1 we can see that A's gain would be 3P plus 5 times 1 minus P. In case B2 we would have 4P plus 1 times 1 minus P, and for B3 we would have 5P minus 1 times 1 minus P. Now these equations are then simplified to 5 minus 2P, 3P plus 1 and 6P minus 1, and put onto a graph as shown as the right hand side. What we've got here is probability on the x-axis going between 0 and 1, and then the expected gain given by those equations for the y-axis. It sometimes helps if you indicate another y-axis going up at 1 as well. The idea now is for A's play safe strategy, it will be the highest point which lies below all of these lines. So what we do is we shade the lowest point of the lines and look for the highest point that we achieve, and that's the point indicated here. Well, that point is where the lines for B2 and B1 intersect, so we can solve the two equations for B1 and B2 to find the value of P, and it turns out here that P comes out to be 4/5. So having done that, we can say therefore A should play A1 with probability 4/5, and A2 with probability 1/5, and A3 never. The value of the game is simply the gain that A will achieve if using that probability for P, and we can work that out from any one of the lines. So it's equal to 5 minus 2P. So when P is equal to 4/5, the value of the game is equal to 5 minus 2 multiplied by 4/5, which is 3 2/5. So the gain that A expects to get is 3 2/5, and therefore B would expect to lose 3 2/5. A similar argument now can be used to work out the strategy for B. You'll notice from our graph that B will either play B1 or B2. There's no point B playing B3 because that will give a worse outcome than playing B2 or B1. So putting in values for Q and 1 minus Q and using a similar argument would work out the strategy for B should that be required. We now illustrate the other thing that you need to be able to do, which is to convert a game or look at a game in terms of a linear programming problem. So this is one of the questions from June 2010 paper, in which you're given a matrix, as it says, for a two-person zero-sum game, and we have the payoff matrix as usual for player A. It says we need to formulate the game as a linear programming for player A and write the constraints as inequalities and define the variables. Well, the first thing to realize is that we can't work with negative values, so we want to make all of the values positive. And to do that, we would need to add some value n which is greater than or equal to the smallest value there, which is 4, negative 4. So we need to add something greater than 4. So let's say 5. And that will produce a new matrix, so a new game in effect. And the numbers are 1, 10, 6, 8, 4, 3, 2, 5, 7. And it's this new game that we're going to look at in terms of the linear programming. So we say let the value of the new game be v. Then we let the probability, or we let pi be equal to the probability that A plays strategy I. So P1 is A1, P2 A2, P3 A3, etc. Our objective then is to maximize the value of the game for A, subject to constraints which are as follows. These are obtained simply from our new table by looking at V minus then the probabilities of P1 multiplied by the number in column 1, P2 multiplied by the number in column 1 also, and P3 multiplied by its element in column 1. So 1, 8 and 2 gives us the first constraint. Doing the same thing with column 2 gives us the second constraint, and likewise column 3 the third constraint. So this is what happens if B plays strategies 1, 2 and 3 in turn. So those are the main constraints. However, we must also remember the non-negativity constraints, which is P1, P2 and P3 must all be greater than or equal to 0. The marking for this question was firstly a method mark for realizing that you had to add some number greater than or equal to 4, a B mark, so no method involved, but a B mark for defining the variables, a B mark for saying what should be maximized, and then method mark for looking at these main constraints, getting at least one right or two correct, or sorry, I beg your pardon, one correct or three correct, and then finally a final A mark as long as everything up to that point was correct, including these non-negativities. So it's not purely for getting the non-negativity constraints, it's actually for everything else being correct. So what's called a CAO, or correct answer only. Looking at a second question now, this time from the June 2011 paper. This is Laura and Sam playing a zero-sum game, and the game is represented by the following payoff matrix for Laura. This simply says find the best strategy for Laura and the value of the game to her. Well, the first thing we should do is just check if there's any dominance for either player, and if we look at Laura's, we'll see that in all cases strategy 3 gives a better payout to Laura than does strategy 1. So we say that 3 dominates 1. So for Laura, row 3 dominates row 1. So Laura is never going to play row 1, and we can literally delete it from our table. Having done that, we should just check if there's a stable solution or not. So first of all, looking at the minimum values in the rows for Laura, we see that those are -2 and -3, so that the maxi-min value is -2. For Sam, we want the maximum values 3, 0 and 2, and then the minimax value of 2. You can see that these are different, so there's no stable solution. So we must look at a mixed strategy. So we let Laura play 1 with probability P, and therefore, I beg your pardon, Laura plays 2 with probability P and plays 3 with probability 1 minus P. Was worth putting these onto the diagram at the top, so we've got P and 1 minus P. We can then look at what happens if Sam plays 1, in which case there is an expected gain for Laura. So Laura's gain is equal to 3P minus 3 times 1 minus P, which is equal to -3 plus 6P. In a similar way, if S plays 2, the gain is then -P plus 0 times 1 minus P, so it's just -P. And if S plays 3, then the gain is -2P plus 2 times 1 minus P, which is equal to 2 minus 4P. Well, taking those one at a time and putting them onto a graph, then we can see the first one starts at -3 and then we'll go up to 3. The second one will start at 0 and come down to -1. And the third one starts at 2 and comes down to -2. Looking at the underneath of that, just shading in, we can see that the best strategy for Laura is at this point here, P, and that's where we have S1 and S2 intersecting. So we need to solve then S1, which is -3 plus 6P, equal to S2, that's -P. Solving that gives 7P equal to 3, or P is equal to 3/7. The value of the game, well, we substitute that into one of those equations. Obviously the easiest one to do that is into -P, so therefore the value is equal to -3/7. So Laura's actually going to lose in this particular game. So what's the strategy? She should play, so this is Laura's strategy, she should play L2, we can say, with probability 3/7, L3 with probability 4/7, and she should never play L1, and the value of the game is -3/7. Well, the marking for this was firstly a method mark for realizing that there was some dominance there, and we could delete row 1. Then a method mark for assigning probabilities to L2 and L3, with A marks for getting the 3 correct lines. Those put correctly onto the graph gave either B2, 1 or 0, depending on how many were correct. The method for then calculating P was M1 and a value A1, and then finally for stating the strategy, A1, and for the value of the game, a further A1. Well, that's the end of this lecture. You can find other lectures for the Decision Maths 2 module, and indeed for other modules, on the website www.furthermaths.org.uk.